Hello students, welcome to Sri Jendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 7 of unit Oscillations. So let's begin with today's class. In today's class we are going to discuss about the simple pendulum. So let's begin with the simple harmonic motion of a simple pendulum. So let's begin with the what simple pendulum is. It is an ideal simple pendulum can be defined as a heavy particle generally considered as a point mass suspended by a weightless, inextensible and twistless string from a perfectly rigid support and allowed to oscillate in a single vertical plane under the gravity. Practically simple pendulum is defined as a small heavy sphere, generally what we call as a bob, that has been suspended by a light and inextensible string from a rigid support. What should be the length of a simple pendulum? When we define the length of a simple pendulum, it is the distance between point of suspension, that means this, and center of gravity of the heavy sphere. So it should be calculated up to this. It is the length of the string plus center of mass, or we should say center of gravity of the sphere. The mass suspended is called as the bob of the pendulum. I hope this is clear. To show that for small oscillations of bob that executes a linear simple harmonic motion, we have made certain assumptions to discuss the motion of an SHM. Let's look at and discuss the that all assumptions. First, it's a bob should be a small, but it should be an heavy. The string is weightless and inextensible. The angular displacement theta of the pendulum must be very small. The length of the pendulum is large. The bob moves along a straight line and its motion is linear SHM. The support is rigid and fixed, and we are going to ignore the air resistance. So air resistance is negligible. Now let's have a look at how simple pendulum will look alike. So let's suppose this is the simple pendulum and this is the bob, and the bob is having mass m and its radius is capital R, its radius is r. So I have hinged the string at this point of time. It's a point of suspension, and this is the distance from point of suspension to the distance which we call as the length of the string. Ideally it is an L plus R. So and in this position the weight, that is what we call as an mg of the bob, is balanced by the tension in the string. So tension is acting in the upward direction, generally it is away from the body, that we know, and mg, that is acting in the downward direction. Yes. So now when I displace this bob over this, yes, when I displace this bob over this, then this will make an angle theta, and if this is the theta then this is t. Yes. So if I write this is an mg, then even this will behave as a theta. So if this is mg, this will be the mg cos theta, and this will be the mg sin theta, and this is mg. I hope this is clear. Is it clear? Is it? Now as we understand that all the theta will be this small, and if sine theta is very small, the force from the trigonometric can be given as, that is, the sine theta is equals to approximately equals to theta. And when I write sine theta, it is the distance, it's an arc by radius, because it's approximately equals to theta, and so that it could be given as x by L. So restoring force could be written, as you can see this, only the restoring force will try to oscillate it. So it's basically mg sine theta, so it's a minus of mg into x by L. When I write it's a minus of mg into x by L, it's a minus of mg by L into x. From this it is the constant which is equals to k, which is equals to mg by L, that is equals to constant. So it is the fr which is equals to minus of kx, and this force is proportional to its displacement from the mean position, and it is directed towards the mean position, so that these two conditions satisfies the equations or the conditions of the SHM. Therefore, the motion of the bob of a simple pendulum is considered under the motion of an SHM. It's a simple harmonic motion for sure. Now we have the relation that it's a force is equals to ma, and this A could be written as Fr by m. Yes, the Fr, the restoring force that we have derived in the previous slide was sorry, it's a minus of mgx divided by ml. Yes, it's a minus of mgx by l, and this m has been written over here. So this has gone, and a, I have been left with the a, which is equals to minus of gx into l, and this a could be written as a is equals to minus of omega square x. From this it's an, if I compare these two relations, a is equals to minus of g by l into x, as well as a is equals to minus of omega square into x. From this I can have the relation which shows it's an omega square which is equals to g by l, and if it is g by l, it's an omega which is equals to under root of g by l. From this is equals to omega is equals to 2 pi by t, and this t is equals to 2 pi under root of l by g. I hope this is clear. When I say it's a t is equals to 2 pi under root l by g, l is the length of the pendulum it's the length of the pendulum from point of suspension from point of suspension to center of gravity of bob, while g it's an acceleration due to gravity. Yes, generally what I can see at this point of time is that it depends on these two things. It is depending on the length of the pendulum from the point of suspension to center of gravity of the bob, and g is the acceleration due to gravity. So now let's check it out that how the time period of the simple pendulum varies. Let's discuss certain cases one by one. First, it's a time period of simple pendulum when point of suspension is accelerating. So let's suppose this is the situation. This is a lift in which pendulum has been hanged, and let's suppose it is moving in upward direction with an acceleration of a1. So that now this is the g which is acting in the downward direction, and let's suppose this lift is moving up. When this lift is moving up, then this time period could be written as this is 2 pi under root of l divided by g plus a. I hope this is clear. Yes, because g is acting in this direction, this is acting in this direction. Next, acceleration down or retarding up, that let's suppose this is the situation where this is a2, let's call this a1. Then what happens? Then g is acting in the downward direction and a2 is acting in the downward direction. So this is equals to t is equals to 2 pi under root of l divided by g minus a2. I hope this is clear. Is it clear? Great. Now let's suppose the situation is something like this, that this is car moving in horizontally direction with acceleration a. What would be the time period? Think and let me know. What was your answer? What was your answer? What do you think? So basically what we are looking for is the g effective. Here acceleration is in this direction, g is in this direction. Basically it's a two vector which align with each other by a 90 degree. So this a effective or I should say G effective, would be equals to root of G square plus A square. So I have put up it over here, and this is equals to T is equals to 2 pi under root of L divided by root of G square plus A square. I hope this is clear. Yes. Now let's suppose this is the situation that pendulum is suspended from the roof of a vehicle that moves freely. This is the situation. This is theta, and let's say this is the pendulum, and this is moving in this direction. So in this situation, whatever the data would be, that this is the G, and in this direction G sine theta will be there. So this A net would be equals to root of G square plus G sine theta whole square plus 2G into G sine theta into bracket cos of 90 plus theta, angle between this two. So when I solve this, it would be under G cos theta, and this time period would be equals to T is equals to 2 pi under root of L divided by G cos theta. I hope you got this. Did you? Did you get this? Are you sure? Are you sure? Any doubts? Is there anything? No? Great. So now let's discuss the situations that this is the situation, this is the lift, and this is the pendulum, and this lift is initially at rest. So in this situation, the time period would be is equals to T is equals to 2 pi root of L by G. Now in the next situation, let's understood that this is the lift, and this is moving upward with acceleration of 2 meter per second square. Then this time period would be equals to 2 pi root of L divided by, as this is acting in the downward direction and this is moving in the upward direction, so this is equals to G plus A, which could be given as 2 pi root of L divided by G plus A, which is equals to 10 plus 2, it's a 12 seconds. Let's understand the third situation. In this situation, it is something like this, and this lift is moving in the downward direction with 2 meter per second square. So in this situation, its a time period would be equals to 2 pi root of L by G minus A, and that would be equals to 2 pi under root of L divided by G, which is 10, this is 2, it's an 8 seconds. I hope this is clear. Next instant is something like this. Yes, this is moving in this direction with a speed of, let's say, 10 meter per second square, and pendulum has been suspended over here. So this is equals to T is equals to 2 pi root of L divided by root of G square plus A square. So this is equals to 2 pi root of L divided by root of G square plus A square, which is equals to 10 square plus 10 square, which is equals to 10 by 10 root 2, sorry, seconds. I hope this is clear. So does it clear each case, every case? Yes, great. Now let's discuss a very interesting case, that this is the situation. Let's say this is the pendulum and it is moving in the downward direction, which is the downward acceleration is given as an A, so that this time period could be given as T is equals to 2 pi under root of L divided by G minus A. Now if this acceleration equals to G, let's say if this is the condition that it is moving in the downward direction with acceleration A equals to G, then what would be the time period? So in this case, time period, it is something like this. This T is equals to 2 pi root of L divided by G minus A, and this is G minus G. So this is equals to 2 pi root of L by 0, and when it's a under root of 0, it's an infinite, or I should say frequency of this will be a 0. Yes, this is free fall of a lift. and so that time period of an pendulum which is performing SHM is infinite. I hope this is clear. So are you done with this all cases? Have you? Have you done with all cases? Even do this case. Do it quickly. It's a theta, and this theta is, let's say, 30 degree. This is car, and in car we have a pendulum. What I can write, it's a t is equals to 2 pi root of L divided by g cos theta. This tends to 2 pi root of L divided by g into cos theta. It's a cos of 30 degree, and when it's a cos of 30 degree, this should be 2 pi root of L divided by g into cos 30. Cos 30 is root 3 by 2. So this is equals to 2 pi root of 2L by root of 3g seconds. This would be the answer. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? So are you done with this kind of questions? We can switch to the other variations. Let's have a look. Let's suppose the situation is that pendulum is placed in vertically electric field. Then the net force on the bob is, yes, let's have a look. Suppose this is the pendulum, and this pendulum has given charge q and mass m already has it. Suppose we have set up an electric field which is in the upward direction. We have an electric field in the upward direction. What would be the situation? The mg that is acting in the downward direction. This is a mg which is acting in the downward direction, and in this cases this f net could be equals to mg plus minus qe. While plus minus, because even this electric field could be in downward direction. Yes, it could be there. So this a net could be given as, this is equals to f net divided by m, and if this a net is equals to given as f net divided by m, then this could be the situation that it would be a g plus minus qe by m. You need to replace only this a net. This is equals to g plus minus qe by m. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts? Do you know? So let's look at the situation where we have a simple pendulum, and this simple pendulum is given a charge plus q, and its mass is m, and the electric field is in this direction. And let's suppose I have been asked to find out the time period. How will we do this? What we understand is that a g is acting in the downward direction. A force due to electric field, that is what we call as an Fe, is even acting on this direction. And as you understand that this Ae would be equals to charge multiplied by electric field divided by mass m, is in the downward direction because the charge is positive 1. So the net force would be equals to m into g plus q into e by m. And from this is t, which is equals to 2 pi root of L divided by g effective. If such is the case, then this will be given as L divided by g plus q into e by m. This is the time period t. I hope this is clear. Is it clear? Is it clear? Great. Now let's suppose the situation is reversed. That means this is the pendulum again, but now in this situation charge is of minus q, and electric field in the same direction that we have in the previous slide. It's an electric field E. So in this case, as this charge is of -1, the force acting on this charge, This is force due to electric field will act in the upward direction, and the G will definitely act in the downward direction. So this F net will be equals to mg minus of QE, which previously it was mg plus QE. So if such is the situation, this time period t could be written as it's a 2 pi root of L by G. And if this is the situation, this will give me L divided by G minus Q into E divided by M. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? Is there? No? Great. Let's look at the next situation. That let's suppose this is the sphere having this is a neutron. Neutron has been used as a bob and its mass is considered as an m. The question is find out time period of the pendulum, and the electric field is acting in the downward direction. This is the direction of electric field. Now what do you think? Just take a time of your 10 minutes, 10 seconds, sorry, and let me know what could be done. In which direction electric force will be acting on this bob, which is made up with neutron only. As you might aware that neutron is chargeless particle, and so no Fe could act on the neutron. So this T should be is equals to 2 pi root of L by G. That's it. You did it. Great job. So always read this, that with which this bob has been made, whether it is a positive charge, whether it is a negative charge, whether it could be a neutron and everything. I hope this is clear. Is it? Great. Let's discuss one more case, that in this situation pendulum is placed in horizontal electric field. So the situation will be something like this. This is the pendulum and this is the direction. This is the direction of electric field. Yes. So this is the G which is acting on the pendulum, and this is the electric field which is acting on the pendulum or in this region, and the acceleration due to this electric field will be given as Q into E divided by M. So this F net, the net force will be equals under root of mg square plus QE whole square, and from this it's an A net. This we are having a two vectors and both are perpendicular to each other. So this A net could be given as under root of G square plus QE by M whole square. So the time period of the same could be given as T is equals to 2 pi under root of L divided by under root of G square plus QE by M whole square. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? So these are the various cases. But these are not the limited cases with which time period changes. Let's take the different variations. This all are the variation in time period due to change in G. It's a gravitational acceleration. So let's see which are the variations we could have. First, due to change in planet. we have this relation, g of particular planet is equals to capital G, which we call as the universal gravitational constant, multiplied by mass of the planet divided by square of the radius. It's square of the radius. It's radius of the planet. So this g on that particular planet would be equals to g into mp divided by rp square. This is g. Second, seconds due to change in height. We have the relation which is gh by g, which is equals to r square divided by r plus h whole square. And the other relation, if h is much less than re, or we can say r, then this gh by g could be given as 1 minus 2h by re. Yes, this all are the variations that we have learned in the gravitation. We are just quickly revise it, and then we will use it. Then we will use its applications. A third variation, that is change in depth. This is gd equals to, this is gt is equals to g into bracket 1 minus d by re. This is change in depth. Next, due to change in density and radius. So as the density and radius changes, it will changes. How? That is given as g directly proportional to the density into radius. This is due to change in the density and the radius. And next is due to rotational effect. Due to rotational effect, this is g due to rotational effect is equals to g minus r omega square cos square lambda. Yes, where lambda was the latitude. Correct. So this all are the variations with which even we can change the time g, and if g changes, time period automatically changes. I hope this is clear. Is it clear? So let's have certain questions based on this. A simple pendulum clock ticks on Earth having time period of t seconds. When this clock has been shifted to a region, shifted to a planet, sorry, having double the mass and half of the radius than Earth. Find time period of clock on that planet. So let's begin. What they have given, they say the simple pendulum clock ticks on Earth having time period of t. So the on the Earth its a time period is t. When this clock has been shifted to a planet having double the mass, that means mass of that planet would be twice of the mass of the Earth, and half of the radius, that means the radius of that planet would be equals to radius of the Earth divided by 2. Find out the time period of clock on that planet. So time period on that planet is required. How will we do this? So basically we understand that there is a variation in the g. So let's just find out the g on that planet with respect to g, and then we can take a ratio and get it done very easily. So let's first work for the G, variation in the G. So we know that it's a G is equals to Gm divided by R square. So if I take a ratio, it's a Gp is to Ge. This G, capital G, has been gone, and this is equals to Mp divided by Rp square multiplied by Me divided by Re square. So this is just the Mp by Me multiplied by Re by Rp whole square. If such is the situation, then we are having Mp is equals to twice of Me. This is twice of Me divided by Me multiplied by Rp by Re. This Rp is equals to Re by 2. So that means Re is equals to 2Rp. It's a 4Rp square divided by Rp square. This and this has gone. This and this has gone. So it's a Gp by Ge. This is equals to 2 4s are 8. This is the ratio of the Gp is to Ge. Now I will take the ratio of the time periods. Let's have a look. This is the time period on that planet to the time period on the Earth. This is equals to length will remain the same. It's a G, it's only the G which varies. It's a Ge is to Gp. So this is equals to Ge is to Gp, that is equals to 1 by 8. This is Tp is to Te. And when it is 1 by 8, under root of 1 by 8, it's a 2 root 2 divided by T. This is the time period on that planet. I hope this is clear. So time period on that planet will be equals to T divided by 2 root 2 seconds. I hope this is clear. Is it? What was your answer? Yes? Is it same? Is it? Are you sure? Great. Let's have the second variation. Let's suppose if time period of the pendulum clock on Earth is 20 seconds. If it has been taken to planet having double the density and 1 by 8th of radius, find time period on that planet. How will you do this? They have said that time period of the pendulum is given, and that time period on that pendulum, or that time period on the Earth is 20 seconds. And we have been asked that it has been taken to a planet having double the density and 1 by 8th of the radius. We need to find out the time period on that planet. How will we do this? Now we understand that time period on the Earth, which is equals to 20 seconds, and time period on that planet is required. One more thing, that it has been taken to planet having double the density. That means density on that planet would be equals to twice of the density of the Earth, and the radius of that planet would be equals to 1 by 8th of the radius. So we need to find out time period on that planet. Great. So let's first work for the GP. Yes, gravitational acceleration on that planet, and then we will switch to time period. So we understand that G directly proportional to the density into radius. So this is G of that planet divided by GE. That is equals to density of planet, radius of planet, divided by density of the Earth, radius of the Earth. So density, it's a twice. If I take a ratio, it's a twice, and if I took a ratio, it's a 1 by 8. So this is equals to 1 by 4. GP is to GE. So now I am having it's a time period on that planet to the time period on the earth, that is equals to g of that planet divided by g of the earth. So gp is to ge, it's a 1 by 4, so ge is to gp, it's a 4 times. So this is ge is equals to 4 times of gp divided by g of that planet. Yes, so this has gone, and this is equals to tp by te. So this is Tp is equals to twice of the time period of the earth. A time period of the earth has been given as a 20 seconds. So time period on that planet would be equals to 2 into 20, which is equals to 40 seconds. I hope that is clear. Is it clear? Is it? Are you sure? Great. Let's look at the next question. You are having two clocks, one based on the spring block system and other based on the simple pendulum. If these clocks have been taken to the moon, which clock can give the correct time? What do you think? How should we deal with this? Basically, they said they are having two different clocks that work on the different principles. One of the clock is based on the spring block system. That spring block system will oscillate, and when it oscillates, it will give us the time period and everything. And the other is based on the simple pendulum. And if these clocks have been taken to the moon, which clock can give the correct time? This is the question. What do you think? What do you think? What is your answer? Yes, we should rely. We should rely on the clock that works on the spring block system. I hope you understand this. Why? Because for simple pendulum system, this time period t is equals to 2 pi root of L by g, and the g of the moon would be equals to 1/6 of the g of the earth. So time period of this clock changes. I hope this is clear. But when I take a case of for spring block system, for spring and block system, this is t, which is equals to 2 pi root of m by k, and nothing has been changed. So it can work efficiently. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? Do you? Do you have any doubts? Any? Is there anything? No? Great. Now, let's look at the next variations. We know that t is equals to 2 pi root of L by G. And if such is the situation, we are having this, that's a t square, which is equals to 4 pi square multiplied by L divided by G. If such is the case, then I can write it's a 2 into delta t by t, that is equals to delta L by L plus delta G by G. Now let's understood that, so from this it's a delta t by t, which could be half into delta L by L plus half into delta G by G. If all the variations if all the variations are less than 5 percentage, then this could be written as delta t by t would be equals to half delta L by L if G is constant, and delta t by t could be written as half into delta G by G if L is constant. But this is applicable only if this variations are less than 5 percentage. If all the variations are greater than 5 percentage, you need to use a manual mechanism to find out this. I hope this is clear. So let's take a questions and you will get a better idea. So they said that if length of the pendulum if the length of the pendulum increases by 4 percentage, find out change in the time period of pendulum. That length of the pendulum has been changed, and if length of this pendulum increases by 4 percentage, we need to find out change in the time period of pendulum. So we are having this, it is a t is equals to 2 pi root of L by G, and as we have derived, it's a delta t by t, that is equals to half into delta L by L. If such is the case, then delta t by t, which is equals to half into delta L by L, which has been given, it's a 4 percentage. So this is change. This is going to be changed by 2 percentage. This is delta t by t. I hope this is clear. Is it? Are you sure? Are you? Great. Let's have a next question. If length of pendulum increases by 4 percentage and acceleration due to gravity increases by 2 percentage, find out change in the time period. Find out change in the time period of pendulum. How will you do this? They said length of the pendulum has been increased by 4 percentage, and this acceleration due to gravity, it has been increases by 2 percentage. So we need to find out the change in the time period of pendulum. So we are having this relation delta t by t, which is equals to half into delta L by L plus minus half into delta G by G. Now why plus minus? Because look at this. Our standard relation is this. It's a T is equals to 2 pi root of L by G. If length of the pendulum increases, that means if L increases, this T is going to increases. And if acceleration due to gravity increases, because this T and G both are inversely proportional to each other, if G is going to increase, this will decrease the T. So if G is increases, sorry, it's a decrease in the T. So my relation will be, it's delta T by T, that is equals to plus half delta L by L minus of half into delta G by G. So this is equals to plus half into delta L by L. This has been increased by 4% and this has been increased by 2%. So it's 1 by 2 into 4 minus half into 2. So this is equals to 1 by 2 into 4, which is equals to 2% minus 1%. This is equals to 1%. This is a delta T by T. I hope this is clear. Is it clear? So it's a delta T by T, which is equals to 1%. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts? No? Great. Ready for next question? Let's have a look. If the length of pendulum, if the length of pendulum increases by 44%, find out change in the time period of pendulum. You need to do this. How will you do this? So as they have changed this, by 44%, and if it has been changed by 44%, we cannot directly apply the rule of variation, that is of less than 5%. So what we need to do is that as it has been increased by 44%, we need to use a manual approach to do this. And to use the manual approach, let's have a look this, that this T is equals to 2 pi root of L by G, and from this it's a T square, which is equals to 4 pi square into bracket L by G. So as I understand that only L, which is keep changing, and G does not have any effect on it, so it's a, let's call this as a T2 square divide by T1 square. This is equals to L2 divide by L1. I will take 1 as an initial, so L1 it's let's call 100, and that has been changed by 44%. Let's call this as a meter. Then new length will be equals to 100 plus 44, which stands to 144 meter. The T1 was 100 and T2 is my requirement initially, and then I will switch to the delta T because they want the change in time period. I hope this is clear. Is it clear? Is it? Are you sure? So now let's look at the situation that this is the T2 square divide by T1 square. This is equals to L2 divide by L1. T2 square divide by T1 square. This is equals to 100 into 100. This is equals to L2, which is equals to 144. L1 it's in 100, so this has gone and this has gone, and this T2 square should be equals to 144 into 100. So this T2 is equals to 12 into 10, which stands to 120. From this initially T1 was 100, this T2 is equals to 120, so there is a change of 20%. So time period time period has increased or time period has increased by 20 percentage. I hope this is clear. Is it clear? Is it? Do you have any doubts up till now? Is there anything? Is there anything? Are you sure? Are you? Do you have any doubts? Is there anything? No? Great. So let's wind up this session over here. This was just the part 1 of the simple pendulum, because we are having still certain variations that is to be done. Yes, so what I want that you just go through this and practice this kind of questions. And before you tune in to the next lecture, please revise this very carefully, because this will help us to get the second lecture done very easily and very smoothly. Please do the needful. Thank you. Have a good day. Take care.